Hello. Today I am discussing a topic called column stores versus row stores. How different are they really? In the realm of database management system, there are two primary data storage architectures that stand out, column stores and row stores. These architectures are fundamentally different in how they organize, store, and retrieve data, each catering to specific types of operations and workloads. Understanding the distinctions between column stores and row stores is crucial for database administrators, system architectures, and software developers as they design system to optimize performance, storage efficiency, and scalability. Row stores. Row-oriented storage systems organize data by rows. This means that all the data associated with a single record is stored together. This approach is traditionally and is commonly used in database optimized for online transaction processing OLTP systems. OLTP systems are characterized by a large number of short online transactions, insert, update, delete, that require quick and efficient access to individual records. Next, column stores. Constantly column-oriented storage systems organize data by columns, storing each column's data together. This method is especially advantageous for online analytic processing (OLAP), where queries often span large datasets but only a subset of the total columns. By storing data in columns, these systems can achieve better compression and performance on read-heavy analytical queries that aggregate on a scale scan large volumes of data. Now we'll see the key differences and advantages. The choice between columnar and row-based storage often hinges on the specific needs of the application, including the type of queries most frequently executed, the nature of the data access patterns, and the overall performance requirements. Row stores excel in environments where transactional integrity and fast writes are crucial, such as in retail sales or banking transactions. On the other hand, column stores are preferred in scenarios where rapid query performance over large datasets is required, such as in data warehousing, big data analytics, and report generation. The fundamental differences in architecture lead each system having unique strengths and weaknesses, particularly concerning performance optimization, storage management, and scalability. A deeper understanding of these distinctions helps in selecting the right database architecture for a given application scenario, ensuring that the system can handle its intended workload efficiency. Now we'll see what is the problem. Here the assumption is that one can obtain the performance benefits of a column store using a row store, either by vertically partitioning the schema or by indexing every column so that columns can be accessed independently. Row store can achieve some of the performance advantages of a column store. Changes must be made to both the storage layer and the query executor to fully obtain the benefits of column-oriented approach. The column stores and row stores example with a dataset introduction. We have taken as ID, name, state, and age. Row store execution. Here, row store execution is done in the disk, and each disk is divided into blocks. In each block, the data is divided into some rows. Here we can see the example of block 1, block 2, block 3, and so on. Each block has some information as in the rows. Column store execution. Here in the column store execution, the data is stored in the disk, and each disk is also divided into the block, and each block the data contains in the column stage. Here we can see in the block 1, block 2, and block 3, and so on. Why is it important? The problem is slightly significant as it proves a false misconception about column stores. People try to utilize the best based on other words without concrete proof. In row stores, data is stored and retrieved one row at a time. This is typically how traditional database operates. It's efficient for transactional processing and operations that involve accessing entire rows of data. In column store, data is stored and retrieved one column at a time. This means that all values for a single column are stored together, which can lead to significant performance improvements for certain types of queries, especially those that involve aggregation or analysis across multiple rows but only require specific columns. Column stores with row stores. Authors outline three alternative physical designs: vertical partitioning, index only plans. In row stores, vertical partitioning involves dividing the table into subsets of rows. Each subset contains a portion of all the columns in the table. This can be useful for optimizing storage and access patterns, especially if some columns are accessed more frequently than others. In column store, vertical partitioning typically refers to dividing the columns themselves into separate physical storage structures. Each partition might contain a subset of columns from the table. This approach can improve query performance by allowing for more efficient access to specific columns, especially in scenarios where queries only require a subset of the available columns. Here is a definition of vertical partitioning in the rows and columns. Here we have taken the ID, employee ID, name and department. Here we are taken the employee ID, name and department ID in the vertical order. Index only plans. In column store where data is organized by column, it's easier to create indexes that cover specific columns. This allows queries to be fulfilled entirely from the index without needing to accessing the main table, leading to faster query execution times. In row store, while index only plans are less common, they can still be achieved by creating composite indexes that cover all the columns required by query. However, since row stores store data by row, the efficiency of index-only plans may not be pronounced as in column stores. Is it challenging? Cons. One problem with the index-only approach is that if a column has no predict on it, the index-only approach requires the index to be scanned to extract the needed values, which can be slower than scanning a heap file. There is no still definite proof that one is better than the other yet. It can provide to be challenged as there are lot of theories out there and no one person can fully understand why it is better than the other. We'll discuss about column oriented execution. Column oriented execution is a strategy primarily associated with column stores as they organize data by column rather than by rows. There is a compression. Data of similar type is grouped together. Compression is easier. Early materialization constructs entity using relevant columns and then applies row store operators. Here we have taken employee ID, name and department ID. What is early materialization? Intermediate results of a query are materialized or computed as early as possible during query execution. This means that all necessary data transformations and computations are performed upfront, potentially resulting in larger temporary datasets. Early materialization is commonly associated with row-oriented execution, where entire rows are retrieved and processed early in the query execution pipeline. With materialization, it means operated on columns. This result in intermediate results are deferred or postponed until later stages of query execution. This means that data transformations and computations are performed on demand, typically closer to the final output stage of a query. Late materialization is often associated with the column-oriented execution, where only the necessary columns are accessed and processed, potentially reducing the size of intermediate data sets. Advantages. Early materialization constructs many tuples at the start. Late materialization constructs a few tuples at the end. Cache line is populated with related data. High data locality of column stores. What are the limitations of the related work? What is the novelty? There is no definite solution of this problem. Extension of previously given theories. Yes, the author has clearly described various implementations. There are a lot of methodologies that can be used. Not all column stores is better than row-based stores. Here is a typical query structure. Just we have a look. Uh, we have taken as nation, C dot nation, S dot nation, and D dot year. Just we are applying the join query on C, S, and D. This is a late materialized query plan where we are using C dot region equals to Asia, D dot year between 1992 to 1997. Invisible join, constructing hash tables, applying each predict to dimension table X list of keys, satisfying predicate, construct hash tables, apply region equals to Asia on customer table. We have taken cust key 1, 2, 3, region as Asia, Europe, and Asia. Nation is China, France, India. We are applying on hash table with the keys 1 and 3 and applying year in 1992, 1997 on data table. Yeah. Here is an invisible join. Use hash tables to locate records in fact table that satisfy predicate. Prob e hash table with each value in foreign key column. Intersect positions list records which satisfy all predict. Fact table order key, cache key, sub key, and order date and revenue. And we'll use the bitwise and fact table tuples that satisfy all joins predicates. Visible join phase 03. Extract dimension table records and execute query. Apply list of satisfying positions to fact tables. Identify foreign key references in the appropriate dimension table. Extract corresponding values. Validation methodology. The validation methodology for column stores versus row stores typically involves assessing various aspects such as data consistency, concurrency control, query performance, and transaction management. It is the baseline performance of C store versus System X compared with materialized view cases of the same system. Features partitioning and multi-threading. There is the column store simulation in a row store. In the figure A, we could see that performance numbers for different variants of the row store by query fight. Here, T is traditional, T of B is traditional bitmap, MV is materialized views, VP is vertical partitioning, and AI is all indexes. In figure B, we'll see that average performance across all queries. Column store simulation in a row store. Why can't we outperform traditional methods T and T of B? Tuple overloads. Tuple overheads. Tuple overhead is quite large in fully vertical partition approach. Must maintain reads of primary keys with each column. Add significant overhead to read operations. Vertical partitioning approach is competitive with row store when few columns are selected. However, as the third number of columns selected grows, tuple headers, waste space, and redundant reads yield inferior performance. Indexing only approach has low per record overhead, but hash joins with fact table are expensive. System X is unable to defer joins until later in the query plan. Cannot retain reads from fact table after joining with the dimension table. Performance. Column store tends to note tuple overhead plus low join cost. Tuple headers are stored separately from data. Column stores rely on position order, not keys or reads. How does it beat RSMV as they have similar IO and no joins are required from the same table? With all else being the same, CS advantage may result from its optimizations, compressions, late materialization, block iteration, invisible join. Column store performance. In figure A, it will describe that performance number of C store by query flight with various optimization removed. The four-letter code indicates the C store configuration. T equals to tuple at a time processing, small t equals to block processing, I equals to invisible join enable, small I equals to disable, C is compression, and small c is disabled, L is late materialization enabled, and small I is equals to disabled. In figure we describe that average performance numbers of C stores across all queries. Conclusion. Authors successfully illustrate attempts to reproduce I/O performance of column stores in row stores were rather fruitless. High tuple reconstruction costs, high per tuple overheads, tuple headers, reads or primary keys. Optimizations of column stores were thoroughly explored, identifying the key advantages over row stores in late materialization and compressions optimizations. Proposed a new join technique is invisible join, extending late materialization via between predicate rewriting. And here are the references. Thank you.